Hello, everyone. So last time in PChem, we started building up a notation for polyatomic systems. Now, this notation started getting a little bit ugly as it included, well, a set of matrices that we've seen below. Where we're looking at is a matrice that represents the Hamiltonian applied to our various atomic orbitals, coefficients of how much of each of our atomic orbitals uh, A, B, and C go into our MOs 1, 2, and 3. And we can set all of this equal to the energies of each of our MOs and the times our overlap matrix, the times our coefficients again. So this general form should look somewhat familiar as it's very much modeled on the ideas of the Schrodinger equation. But it turns out that when we try and start expanding this to full polyatomic systems, it can start to get a little bit messy. And so what we're going to be doing today is focusing in on one relatively small example system of how we can apply these equations, and one of the more common and simpler set of approximations we can apply to this system. So what we're going to be looking at is a pi system for butadiene. Now, one of the reasons why we like applying our simple MO models to pi systems is our overlap matrices are relatively small compared to sigma systems, as we've seen before. And it usually involves quite a few less numbers of orbitals. As when I'm working with butadiene, all I have is 4 atomic orbitals, which I will label A, B, C, and D, and that gives me 4 electrons to fill my system with. So where we're going to start is going to be a classic point, building up our Hamiltonian matrice. So just as a reminder, this is going to be a set of Coulombic integrals. So that's the Hamiltonian applied to a single atomic orbital, and our resonance integrals, which is applying to the overlap in between the two systems. So now one of the tricks when we go to full polyatomic systems is that when I build up this Hamiltonian, I have to account for every single possible energy overlap. So this means all of the possibilities of A overlapping with B, C, and D, and the reverse, all the possibilities of B with A, all the possibilities of C with A, and D with A. So not too surprising, we're going to find a symmetric matrix where these two elements should be identical, and the same thing with these two and these two. All right, so that is definitely going to help our cause. We also know that along this diagonal term, we have our Coulombic integrals, and we already developed a set of equations we can use to approximate these values. If you need a reminder of that, please go ahead and revisit the lecture on electronegativity. But you'll notice this does give us a 16 by 16 matrice, which is going to give us quite a bit of problems to try and actively solve. So in practice, we're going to want to find a good way to truncate this matrix, set as many of these values down to known quantities. We already have a head start with the diagonal elements, but we still have these other 12 elements, and even if you account for symmetrics, we still have 6 more Hamiltonians to solve. So really one of the hearts of quantum methods and polyatomic systems is finding reasonable approximations to help make solving all of these various Hamiltonians a lot easier. So what we can then do is take our butadiene, set up our full set of equations, because don't forget, I've got not just one 4x4 matrice, but 1, 2, 3, 4 different 4x4 matrices, a 5th if you account for the fact the coefficients show up twice. This is going to be a bit of an ugly problem. So what we're going to want to do is find as many terms that we can drop as possible. So we're going to be looking at one of the simplest sets of approximations, which also means it tends to be one of the more severe sets as it's going to make this problem a lot more simpler, meaning we neglect a lot of things. And that's going to be the Hückel approximation, which focuses on three major assumptions, all of varying quality and all of varying effectiveness. So one of the first approximations we're going to make is one that we've seen before, and that's the zero overlap approximation. So this is the idea that I'm going to set all of my overlap integrals, so over here on our overlap matrix, I'm going to more or less set all of my overlap integrals to the Kronecker delta, which means an orbital will completely overlap with itself. This one is a sure thing. So I can set all of my diagonal elements equal to 1. And then I'm going to say, well, these are p orbitals. I'm looking at a pi system. And if you may have noted from the last quiz, the overlap in between adjacent pi orbitals is actually pretty low. Let's just set it to 0. So what this ends up producing is that this overlap matrix will have elements of 1 along the diagonal and elements of 0 on the off diagonals. And we're going to see later that this is a huge advantage in simplifying our equations. The next one is not too bad. So this is going to be that all resonance integrals between non-neighbors are set to 0. So again, let's put this more in terms of kind of energetic terms. Let's say if I'm looking at the energy of atom A, it's going to have some sort of resonance with atom B. But what I'm going to say is that anything that's sufficiently far away, so C or D, there's going to be no energy of interaction. Well, when you're looking at, say, pi systems, maybe this isn't too bad, maybe it's not too great, but it definitely has some advantages. Where you have to watch out for on this guy is when you have systems that, say, bend around on themselves, that you can have non-bonding interactions between non-adjacent atoms. Otherwise, there are far worse approximations. So the last of our three major approximations is that all of our remaining resonance integrals, so this is the interaction of, say, A with B, B with A, and B with C, all of these are going to be set to the same exact value. So again, since these are resonance integrals, we're going to fall back on our old notation. So we're just going to give this our classic resonance integral, beta value. And again, one of the reasons we do this is that beta is a very big pain in the butt to solve, as it's a little bit more non-intuitive. So we'll often choose either an arbitrary value of beta that we can then try and determine later, or as we've done before, take a reasonable value like -1 eV. So this is probably the most severe approximation. In a system like butadiene, it's actually not too bad, because the amount of interaction in between any carbon atom and any other carbon atom is going to be actually pretty similar, because they're all carbon atoms. It's a conjugated chain. They all have the same exact distances. This isn't the worst approximation for conjugated carbon systems. However, as soon as I try to throw a heteroatom in there, a nitrogen or an oxygen, then we start running into some issues, as they're a little bit as they start to become a bit more non-equivalent. In addition, you also have to watch out for if the distances start differing in between the three bonds, because again, at this point, we have this non-equivalency, and this approximation doesn't become quite so nice. So what we can do is use these set of approximations and try and simplify our set of equations up here. So one of the things I'm going to do is, you'll notice that none of these approximations touch our coefficient integral. So this is more or less the composition of each of our molecular orbitals and how much of each atomic orbital goes into them. So molecular orbital 1 is in the first column, molecular orbital 2 in the second column, so on and so forth. As we walk down, that's going to give the contributions of atomic orbital A, B, C, and D. But this, so far, none of our approximations have really touched it. So I'm going to condense this down to our C, and we're going to focus a lot more on these three matrices. So we can go ahead and again make another nice approximation, since all four of these atoms are more or less the same system, so they're all the orbitals I'm looking at are all carbon px or py orbitals, so they're all identical. So I'm going to make another approximation that they all have the same energy of alpha. And now using that, I'm going to form my approximate forms of my Hamiltonian, my energy, and my overlap matrices. So let's walk through each of these matrices individually. So my Hamiltonian, so atomic orbital A interacting with A is going to give me my Coulombic integral alpha. And the same thing with B, C with C, and D with D. So all of my diagonal elements are the orbital interacting with itself, and so it has elements of my Coulombic integral alpha. Now my resonance integrals come in two flavors. So A with B, because the only neighbor of A is B, is going to have a value of beta. The interaction of A with C and D goes to 0. B interacts with itself with a Coulombic integral and interacts with alpha and C as neighbors with the resonance integral and doesn't interact with D at all. And that's more or less what each of these matrices elements are going to be telling me. And so with that, I get the energies of each of the orbitals interacting with each other. And that's the idea of the Hamiltonian. Now, the energy matrix is actually fairly straightforward. The first element gives me the energy of my first molecular orbital, second molecular orbital, third molecular orbital, and fourth molecular orbital. This one is fairly nice as all of the values are on the diagonal, which we'll make use of later. But again, this was our definition of the energy matrix as we developed last lecture. Now, one of the marvelous things that ended up happening was our approximations for the overlap matrices, where we assumed that we have a normalized atomic orbitals. So the interaction of any atomic orbital with itself is going to be 1. And then we're assuming that we get minimal overlap in between neighbors. So all of the non-diagonal elements go to 0. Now, anyone who's familiar with matrices may notice that this is a very special matrice, and it's given a very special name. It's called the unit matrix. And the reason why is if I multiply the unit matrix times any other matrix, it gives me my starting matrix back. So my unit matrix, which is now what my overlap matrix has become, times C will just give me C back. This is the matrix equivalent of 1. So anytime you need to, say, multiply by 1, you go ahead and just throw in the unit matrix. It's also fairly common in being able to turn scalar values to a matrix because I can multiply any scalar value, say E, B, or alpha, times this matrix and then just get values on the diagonal, which we'll make use of later. But one of the beautiful parts is when I've got a series of matrix multiplications, it means if the unit matrix shows up at any point, I can just ignore it and drop it out, which becomes seriously useful as I can now condense my form by dropping out the alpha matrix, the overlap matrix, and now I get the Hamiltonian, essentially equaling the energy matrix. This is a huge advantage. Now, it is worth noting that each of these matrices is being multiplied by the coefficients, the coefficient matrix. But since it shows up on each side, I can actually drop it out entirely. But another more common rewriting of this form is I can multiply each side by the inverse of the coefficient matrix. So if you need a refresher for matrices, the inverse of a coefficient matrix is literally where you replace columns with rows and rows with columns. But for our purposes, what's actually fairly useful about this is that this form of multiplying a matrix by another matrix and its inverse is another way of saying that I've taken my Hamiltonian times a wave function and its complex conjugate to get my energy out. Now, this actually has two major purposes. First of all, it will diagonalize my Hamiltonian matrix to make sure that all the values left are along the diagonal, which will let me set it equivalent to my energy matrix. So what we're often interested in is what are going to be the values on the diagonal, because that's going to give me my energies, but also what's going to be the coefficients or molecular orbitals that perform that function. Now, one of the other things that you may notice at this point is I have the complex conjugate of a wave function times the Hamiltonian times the wave function gives me the energy. What we just wrote is the matrix version of the Schrodinger equation. And we can treat it very much as such. And this is actually a very powerful tool, as what it lets me do is replace big complicated integrals with lots of smaller linear algebra equations, which is a big advantage. But this also means that if I'm able to diagonalize my Hamiltonian matrix, I can set it equal to my energy matrix. So again, this diagonalized form is telling me that only the diagonal elements have non-zero values. So what I need to do is find a good way to diagonalize my Hamiltonian matrix, which will involve me trying to determine what wave functions do this. And then the diagonal elements can be set equal to my molecular orbital energies. So we need a good way to diagonalize our new simplified Hamiltonian. So we're going to start by doing this a little bit by hand before we start falling back to our good friend, the computer, to illustrate some fun points of the Hamiltonian matrix. So one of the first things we can do is start with our Hamiltonian matrix and separate it out into the Coulombic integrals and the resonance integrals. So our Coulombic integrals just occur along the diagonal. So I can pull out the unit matrix times my Coulombic integral, because it has the same value for each of my diagonal elements, which is a wonderful thing. And then all this leaves behind is going to be my resonance integrals, which, because I'm making the Hückel approximation, only occur on these kind of adjacent elements. So what we can then do is, first of all, realize that this is the unit matrix, and then second, realize that all I have is the only elements on my resonance integral form is the indeed resonance integral. So I can pull this out and express my Hamiltonian matrix as my Coulombic integral times the unit matrix, which is already diagonalized, plus my resonance integral times this new matrix, we can refer to it as M. So now if I'm going to diagonalize this form, the only matrix I actually need to diagonalize, already diagonalized, scalar value, is just this guy. So it turns out that in order to diagonalize this form, this is called an eigenvalue eigenvector problem. Yes, these are the same eigenvalues and eigenvectors we've been dealing with, now in their traditional linear algebra nomenclature. So you can do this by hand, but let's be honest, we live in the modern era. So what we can make use of is computer software. So you can do this with specialized mathematical programs, or I personally like using Mathematica, which is a very friendly form of diagonalizing the matrix, and we can turn our matrix M into our new diagonalized form. So what we can then do is, having this new value M, we can combine it with our Coulombic integrals to regenerate a diagonalized form of our Hamiltonian. And what you're going to find is that now all of the non-diagonal elements went to 0, and all I have is 4 values. Well, those 4 values are going to represent my 4 energy values. So these are my eigenvalues of energy, or my molecular orbital energies. So my first MO will have an energy of my Coulombic integral plus 1.62 times my resonance integral. And now remember, our resonance integrals tend to be negative values. So this is going to provide me my lowest energy orbital, or my first molecular orbital energy. And then we have our second MO energy, which is slightly higher in energy as it goes up by 0.62. And now we end up generating, by the time we hit our third MO, energies that are actually higher than our starting atomic orbitals, first by a little and then by a lot. And now what you may notice is we see very similar trends as we've seen for our smaller diatomic systems. I took 4 atomic orbitals, I mix them up, I get 4 molecular orbitals. 2 go down, 2 go up. And especially as tends to happen when we make a zero overlap approximation, each one of my orbitals that goes down corresponds to another orbital that went up just as much. So we have our 2 paired bonding and anti-bonding, and then the much smaller bonding and anti-bonding forms. And we'll take a look at this visually a little bit later, but I do want to comment on how we'll typically do this in practice. Instead of taking this long step-by-step approach, we're going to do most of this usually using a computer solver. So I'll post a tutorial video a little bit later, but you can do this in Mathematica with the command eigenvalues. Watch out, it needs to be plural and it needs to have a capital. If you run into problems, first of all, Mathematica has a wonderful support system, and then second, feel free to let me know if you have any questions. Now, one of the things that also is fairly important to remember is that when we diagonalize the system, it turned out that it took very specific matrices to diagonalize the system. So this will correspond to our eigenvalues having a specific coefficient matrix of C. So you can end up producing this once you have your eigenvalue energies. And so for butadiene, it gives you this rather big, kind of ugly looking matrice. But it turns out that this actually has a lot of significant meaning. So each row of this matrice corresponds to the amount of atomic orbital character in each of my 4 MOs. Sorry, each column of the matrice corresponds to the amount of energy of each of my 4 MOs. So in my first system, my first MO has a little bit of contribution from my from A and D on my atomic orbitals, and a lot more contribution from B and C. My second MO has a little, and all of them are in phase. My second of MO has a lot of more contribution from A and D, but you'll notice that now A and B are in phase and C and D are in phase. So this is actually kind of interesting because this molecular orbital relatively corresponds to the picture we traditionally draw of butadiene, where we have more or less a double bond localized in between A and B and C and D, where we don't have where we'd have a node running in between. And then by the time we hit the third MO, now B and C are in phase and A and D are out of phase. And again, with varying amounts of contribution. So what's possible is we can then correspond each of our energy eigenvalues, which each of these atomic molecular orbital configurations. So each of our eigenvalue energies is corresponding to an eigenvector molecular orbital. Now it's possible to obtain these as set pairs, again, using functions in Mathematica, where we can apply eigenvalues to get the energies and eigenfunctions to generate our eigenvectors or our molecular orbitals. And so what we can do is start to pair these energies and their corresponding molecular orbitals. So our atomic orbital 1 starts centered around our atomic orbital energies and then is lowered by a relative amount corresponding to the degree of overlap between adjacent carbon atoms. And again, is going to be mostly composed of atomic orbitals B and C, with a little bit of A and D, with everybody acting in phase. The second molecular orbital is again going to be slightly lowered compared to the atomic orbitals, with a ratio relative to the resonance integral. And again, we'll have A and B in phase and C and D in phase, but a node running in between. And you can continue this to the third and fourth MO. So right now, I've given you essentially a whole bunch of numbers. Let's go ahead and try and visualize these to give us a little bit more context of how this system looks like when all put together. So what we end up finding is something that looks rather like what we talked about so far with diatomic systems, but now I've scaled it up to be spread over 4 atoms instead of 2. So I'm blending together 4 atomic orbitals, and I'm going to have one orbital that goes way down in energy, one that goes way up. And the one that goes way down has everybody lined up in phase. So there's going to be no nodes running in between, which is what provides it being so low in energy. Similarly, I get the highest energy species by having as many nodes possible. So that means I'm going to have a node in between each atom center, which means electrons are not going to be localized in between the atoms, which is going to provide a lot more repulsive character. So this is our ultimate bonding orbital, and this is our ultimate anti-bonding orbital. Now let's put them all together. So as I go up from the first molecular orbital to the second, what I've done is I've added a single node. And when I added a single node, the energy went up by about 1 of the resonance integral. And then I added in a second node. So now I've got 2 nodes, which is going to increase the repulsive character. And it's going to end up increasing by about another interval of the resonance integral. So every time I increase the number of nodes, I'm going to increase the energy of the MO. And what's worth noting is that if you have when you have no nodes, lowest energy, 1 node on 4 orbitals, or 1 node versus 2 mixes, you end up with still energy lower than where you started. But as soon as you have more nodes than you have constructive overlaps, that's the point when I go from favorable with respect to my starting orbitals to unfavorable. And this is a very important point when we're trying to evaluate the stability of a system. We want our system to be net lower in energy than when we started. That's what makes good bonds. And so what we can do is try and get an idea of the energies of a system in, say, the bonding versus the non-bonding form by counting up the energy of each of the occupied electrons. So if I wanted to find the electronic energy for this whole butadiene system, what I would do is I would take the energies of each of the electrons. So in this case, butadiene brings 4 electrons to the table. So 2 electrons little technical difficulties. So 2 of the electrons have this energy, and 2 of the electrons will have this energy, when none of the electrons are going to be occupying these upper states. So you would take 2 times this energy plus 2 times this energy to get the overall energy. And as you'll notice, this is going to give us a value significantly lower than where we started at 4 alpha. And putting this all together, we can quickly determine the energy of our overall system. So hopefully this kind of makes sense of the Hückel approximation. It makes some fairly severe descriptions of how we treat molecular orbital systems. It's pretty good when looking at simple systems like conjugated pi systems where all of the bonds are of one type. However, if we try and extend this to sigma systems or into more heterogeneous systems, we start running into a little bit more difficulty. But for now, it gives very good qualitative descriptions of what our MOs look like. And now you can start to see where all those MOs we generated in general chemistry really came from. So next time, I'm going to give a real brief crash course on the various ways that more advanced computational methods look at treating these systems. Till then, take care and stay healthy.